Hey, good afternoon, everyone. I hope you are doing all right and hoping you can hear me. Oh, my microphone is a little bit far, so let me grab that. Okay, so now it's close. So, last class, we talked about how to solve problems when there are. Oh, hold on. I think we did not quite finish those slides last time. So I think I need to pull those slides here. So just like I was saying, last class, we talked about how to solve problems where there are multiple resistors, and they could be in series, parallel, or combination of both. Okay. So here is one such example. You see over here, these two. Come on. These two seems to be parallel with each other, but this one is in series. So we looked at these three registers last class. There's this kind of combination. But over here, what do you see is there is another one that is parallel to all of these. Okay. So how do we figure out whether something is parallel or in series? So we need to keep in mind that same current flows through the series connection. And for the parallel connection, what happens? Current splits, just like it doing here. This current is coming here, and it splits here. And these two current just combines back over there, right? And the voltage over here and voltage over there are going to be same in parallel, okay? So if we keep that, then analyzing, let's say, a fairly complicated circuit like this uh, becomes, not that bad. So these two are in parallel, so that we see by just looking at how these currents are recombining here, and then they start flowing. So now whatever current was arriving here that split, see those current basically recombined here. And since there are no other path, what happens? Whatever amount of current that was entering this point, when they recombine, it's going to be same amount of current. For example, if this is I1, over here it's going to be I1. But in the intermediate, for example, it could be I2 here, I3 here. But when they combine back here, it becomes I1. Okay. So now it was I1 here, and when it's entering over there in this resistor, it is I1 again. So what that means, in this combination and this one over here, the same amount of current is flowing. Although that amount of current is branching over here, the same is flowing. So what that means is that this one is in series with not just this one, but it is in series with combination of both of these. So that's how we need to look. Okay. So that's how the current is splitting and combining. And then what happens over here, whatever current is starting here. So that one basically recombines here. And let's say if there is one battery connected over there, maybe I should flip the battery because I drew current entering from here. So that means current must be starting from there, right? So over here, this full connection is not shown, just the combination of registers. So we don't need to know full story to just figure out what the equivalent resistance is, okay? And that's what this is talking about. So these two are in parallel. So let's name these resistors. Let's say this is R1, this is R2, and this is R3, and this is, let's say, R4. Okay. So first what we need to find is, let's say, find the equivalent of these two. So that means 1 over R, 1, 2. See, this is not 12. You do not want to read like 12, but rather read that as the equivalent of resistor 1 and resistor 2. And you may be thinking, okay, why we are not writing R equivalent? Yeah, we may, but R equivalent usually means the equivalent of all the combination, okay? So these are intermediate equivalent, okay? So that's why I'm giving this different name for them. So that way I can write this, okay? And so that R12 becomes R1, R2, R1 plus R2. So adding this fraction and then flipping it because R12 is in denominator over there gives us this. Okay. So it's basically when they are 2, we just multiply both of them and then divide by the sum. So 90 plus 45. Okay. So that gives us R12. So maybe someone can punch that in calculator and type that on the Zoom. So now with that, our new circuit gonna look something like this. So we have R3 here, and now R12 is in series with R3. However, R4 is still there, right? So like that. So now next step, what we can do is that this R3 and R12. So what's the equivalent of that? By writing equivalent of that, we can draw a circuit like this. I'm keeping R4, now replacing these two by 1. And what should I call? Maybe R1, 2, 3. Okay. So now this becomes something like this. Now eventually these two are in parallel. So before I forget to add them, so let me write it down. So R123 is R12 plus R3. So I don't need reciprocal for this because they are in series. Okay. Okay, so someone calculated this. Hopefully that is correct because I have only one response. To make sure that's correct, we need more than one to verify everyone is getting that. Okay, so that's that. So that means if that is 30, then this 10 gonna be 40. Yeah, this is 1/3 of the larger one is 30. Okay. So anyway, so that becomes 30 plus 10, 40, if that is correct. Okay. So now we have this circuit and they are in parallel. So for this circuit now, let's say now I can write 1 over R equivalent because that's going to be the overall resistance of the whole combination, right? So I can write that as a 1 over R, 1, 2, 3 plus 1 over R4. So that means 1 over 40 plus 1 over 25. So R equivalent in this case is going to be 40 times 25 over 40 plus 25. Okay. So that's how we can do it. Okay. So sometimes what may happen is that we may see something like this. See here? And by just looking at it, it's hard to tell which one is in series and which one is in parallel and so on, right? So in that case, if we redraw that, so I'm writing equal sign. So if I stretch this and bring these, let's say on this side, see what do we see here? So this is in series with all of these because that's how the current gonna come and branch from there and then eventually recombine. And so now we have this end and that end over there. So that means in between what happens? This one comes here and goes with that. So these two are in series and this one is in parallel with each of these two, right? So when I redraw by looking at that, this is what I find. R3 and R4, they are in series with each other. And the combination is in parallel with R2, okay? And you have this R1 in series with all of those. So how do we reduce them? So here, these are in series, so it's going to be easy to combine them, R3, 4, for example, let's say. And then now R3, 4 and R2, they are in parallel. So if I were to redraw that circuit, so R1 is there, and then R3, 4 is over there, and then R2 is over there. So now R3 and R4 is saying, okay, this is 4 and 2. So that means I can calculate by just multiplying these two and dividing by the sum, right? So 8/6. Oh, hold on. R3 and R4, they are 2 each of those. My bad. Oh. So that means 2. So that means it's going to be 4 then. Oh, it was in series. And why was I doing parallel calculation to begin with? So anyway, so that's 4. And now R2 is also 4. And both of these are in parallel with each other. So when two resistors that are in parallel and they are equal, that means the equivalent becomes half that we learned last time. If you don't, and then use formula and find it out, then this is going to be 2 ohm. So now these two are in series. So this is like, say this 2 ohm is R2, 3, 4. So that is 2 ohm. And the sum of these two are going to be 3 ohm. So now finally we have our equivalent, which is sum of R1 and R2, 3, 4, and that gives us 3 ohm. So sometimes things may look something like this funky, but if we can rearrange them by seeing what's going on, that's going to look familiar. Okay. So why do we need to connect these something like this? So one reason maybe sometimes you may need, let's say, 3 ohm resistor, but you may not have 3 ohm. You have 1 ohm and 2 ohm, but you don't have 3 ohms. Then what do? You put them in series, for example, right? And let's say if you need 7.5 ohm resistor, but you have 15 ohm, another one 15 ohm. So if you put them in parallel, then the combination gonna be same as putting 7.5 ohm and so on. Okay. So anyway, so that's why, you may see something like that. But of course, the main reason is that we want a particular voltage in a particular section so that, we can feed that to some device, and that device works with that much voltage. So for example, let's say you have three different devices. One uses 12 volt, another uses 20 volt, another uses 100 volts, right? So by designing this kind of circuit, what you can do is you can provide exactly needed voltage. So there are several uses, okay? So for the test, I won't be, just finding the equivalent is not that bad. So finding current and voltages, you want to learn how to do that when you have two in parallel or in series, and then one series and two parallel up to that. So I will test you up to that kind of complicated when I ask you to find voltage or current through each of these resistors, okay? But if you see something like this, don't get confused. It is basically same thing. So now, see, so far, what we have is we are assuming that there going to be only one battery or source that is supplying current or something like that. But in some circuits, what's going to happen is there may be another battery sitting there, for example, okay? Between C and B. And so something like this, let's say there is a battery over there, another battery, right? If this battery shows up in the middle, then our series and parallel thing may not work. This series may still work, but now we cannot say this combination is in parallel with R2 because there is another source over there. Okay, so how do we analyze that kind of circuit? So there is more general way of doing it. That's given by Kirchhoff's rules, okay? And that's what we're going to be talking. So these Kirchhoff's rules can be applied to any circuits, okay? Whether there is just one source or there are multiple sources. So the reduction, series and parallel, can be done only when there is only one source, only one battery connected to that jungle of resistors. But if there are more than one batteries, then we cannot just always reduce that to series and parallel. So in that case, we need to remember this rule. And these rules are nothing but it's the conservation of charge and conservation of energy. So conservation means total remains constant. Total final is equal to total initial, something like that, right? So that's how we've been writing the conservation rules: conservation of energy, conservation of momentum, and so on. So conservation of charge also means total number of charges before and total number of charges after must be same, because those charges are still on those, they haven't escaped from the circuit, okay? Nobody ate the charge, okay? Nobody ate the charge, okay? Nobody stole the charges in a circuit, okay? So its charge is moving, but when we say potential drops, that means, remember, potential is related to energy. So energy of that thing changes. So sometimes they are moving faster, sometimes they are moving slower, but they are still there, okay? All of them are there. So some of these idea we already used in last class as well, but here we are formalizing. It's kind of common sense thing as well. So for example, if there are these, current entering some point here and going something like that, right? So this is the junction over there. And here, this is the junction. So in this junction, if we pay attention, what do we see? There is I1 current is coming into the junction, and I4 is also coming into the junction. So we can say, okay, how much total current is coming into the junction or entering the junction? That means it's the sum of these two. It's like saying, okay, there are water flowing through two pipes. They are coming through the pipe, and you join those pipes with the bigger pipe, let's say. So that means how much total water going to be flowing in? That's going to be the sum of the flow from one pipe and another pipe. The current flow is like a water flow or flow of traffic in a road. Okay, they're basically same thing. So it doesn't have to be very complicated. It's the flow of charges. And in solid objects, it's the flow of electrons. That's what the currents are, right? So whatever arrive there, they must leave there because they do not want to sleep there. That, you know, so car, we may stop. As a person, we may stop, but these, as long as there is electric field, they are just moving, keeps moving. They don't fall asleep. They don't just vanish in the junction, okay? So whatever enters, they have to leave. So that means it's a conservation of charge. And that's why it is like that, okay? So if this was, let's say, 5, then instead of I1, it would be I5 plus R4. I4 is equal to I2 plus I3. Okay, simple. And if you like, you can rearrange them. So bring I2 on this side, I3 on this side. So both of them are going to be negative. And what that means? This is the sum, I1 and I4 is sum of that's entering, okay, coming into the junction. And these two are the one that's leaving the junction. So difference between them is 0. So total remains unchanged. That's another way of saying it, okay? So that is called junction rule. And now, did I write it as a junction rule? Okay, let's add that here, and this is junction rule. So this is junction rule. And then another one is loop rule. So here there is not a loop. You see, none of these are making loop based on what we can see over here. But over here, you see there is a loop. Okay. So it has to be a complete loop. So in a complete loop, what happens is that in some places, for example, where there is a source, the electrons gain the energy, they acquire the energy, okay, energy increases. And then when they pass through the resistor, they lose the energy, they slow down, okay? So in this case, these energies, we don't write in terms of kinetic energy, rather we write in terms of potential energy. And even more, since these are electrons, we know charge. So if we know potential difference, we know how much energy is there. The charge of an electrons times delta V. So that much is energy. So rather than writing E times delta V or Q times delta V, we simply write delta V, okay? That way we know how much energy is changing. So this is what we call potential difference. So change in potential gives us change in energy as well, okay? So now when we take account of all the energy that's changing, and there is also another resistor over there. So when we take account of all these, then in a loop, total, increase and decrease. So overall should be 0. So it's like saying, okay, when we start from here, let's say for the gravitational potential energy from some height, and then go higher. And then when we come back down here, what happens? When it's going higher, its gravitational potential energy is increasing. And then once it starts coming down, its gravitational potential energy decreases. By the time it arrives here, the change is 0 now. It's like it went into a loop. It went up and came back to the same place, right? So same idea. So now the challenge here is to figure out which one to be positive, which one is negative. right? So when it's increasing, we say it's a positive, and when it's decreasing, it's a negative. Easy enough, right? So let's talk a little bit more about that. Okay. So sum of potential differences must be zero in a loop. That's what the loop rule says. So before we start counting about the potential difference, let's make sure that we understand the junction rule. So let me open the clicker. Turns out I haven't started clicker yet. Okay, here you go. And you have 1 minute and 30 seconds for this. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see how did we do here. So we have all of those. Okay. All choices get some love. Okay. So a bit more for B. So here is a junction. So in the junction, 2 ampere is arriving here, and over here 1 ampere is leaving there. So there is 1 ampere missing somewhere that must be going through this one here. So when it arrives this section, it is going 1 ampere to the right. Okay, so looks like B is correct answer. Okay. See here, this would have been 3 ampere if this 1 ampere was also arriving here, if it was like that. Okay. But it's leaving. So this is also leaving. So that means the one that's entering 2 ampere must be equal to 2 of those leaving means 1 ampere plus I, that one there. So that's why I is 1 ampere. Okay. So now let's learn how to count positive or negative, or yeah, when we are going through the loop. So while using loop rule, what should we do? So here is my suggestion here. Okay. So choose a loop and then choose a convenient point. Say A. A is here. So loop. So you can go this way, clockwise, or counterclockwise. Okay. Either way is fine. Okay. So let's say we are going clockwise. So this is called loop. Okay. And there can be more than one loop. So in that case, you can say loop number 1, loop number 2, and so on. Okay. And now let's start from here. Okay. So that's the first thing you want to do. So you look at the complex circuit and think them in terms of loops. Okay. One loop, another loop, and so on. So for convenience, here is just one, but we'll also look at the circuits that have more than one loop. So this is loop. Recall potential increases when you go from negative to positive terminal of battery. So for example, we may say this is 0 and this is 12, right? That's how we've been using. So positive is higher. Positive potential is higher than negative potential. So that means here potential is increasing. Okay, so this is higher. Final. So I'm just looking at battery here, this EMF. Okay, so final point. So since you started here, see in the loop, see you are going clockwise. So that means you're not going down, rather you are going up in the battery here. So you are going from negative to positive. So in that case, what's happening is final value of potential is larger than the initial value. So the difference being final minus initial, right? Always difference is final minus initial. So when final is higher than initial, means lower, that means this difference is positive. Okay, so that's why the sign here is positive. Okay, so when I'm doing this, what do I do? Okay, there is 12 volt. Is this 12 volt positive or negative? So now we know it is positive 12 volt. And for what? For this clockwise loop starting from here. Okay, so that is important. If you were to go other way around, then the same thing would be negative. So that's why choosing loop is important. Okay. Now, another thing you want to keep in mind, just like we need to keep that in mind, similarly, current flows from higher to lower potential. Just like water falls from higher height to lower height, similarly, current falls from or flows through, it goes in the direction of higher to lower potential. So that means here, when we say, okay, in this case, in the circuit, current is flowing like this. So that means current is flowing like that over there, okay, in the resistor. So in that case, what's happening is current is flowing in that direction. So that means this is higher and this is lower. Okay. So now this, since we are going this way, see our loop is clockwise. So since we are going like that, so what happens here is that final is the lower one. Final is lower and this initial is higher. Just looking at over here across this register denoted by lowercase r in this case. So that means what's the sign of this? Okay, so current is flowing that direction means it's lower. So lower minus higher. Here higher minus lower was positive. Now lower minus higher going to be negative. So this is going to be negative. So how much is potential drop over there? And here it is I current flowing through is I, because see this is, they are all in series in a loop, right? So same current is flowing here. So that means current is I, multiply that by resistance, that's going to give you potential difference. And this is negative over here. Okay. And now we come back here. We are saying that is delta V. Okay. So how much is delta V? We can also write that as I times R, uppercase R in this case. So again, it's going like this. So it is falling. So when your loop is going in the direction of current flow, looks like that's going to result the negative potential drop. Okay. So it's going to be I times R. So now, how do I write this then? So how do we complete this sum of potentials? That left-hand side. So we say, okay, oops, yeah, that is. So let's say positive EMF or 12 volts, okay? And then minus I times R. And then this is also negative I times uppercase R. So this sum of three. So there are three elements in the circuit, two resistors and one source, okay? So because of that, you get three terms, and that is equal to 0. So that's how we write it. Now let's solve this one for I, current, okay? So if I write this, let's move the term containing I or current in one side. So it becomes that. So if I factor I out, what's going to happen? R plus R, and that is equal to EMF. So I is EMF divided by R plus. So see, this result is same as using our series combination. Let's say here, these two resistors are in series, right? So that means R equivalent in this case is R plus R. So that's why the current is this EMF divided by R plus R. So we can use both methods here because there is only one source, okay? So either method gives you same result, and it should be, right? You cannot just use one rule, one law and the other law and get two different results. Physics is same. Result should be same no matter what rule or law you apply. If your result is different, either you made mistake or your rule is wrong, okay? So anyway, so that's that. So now I think I have a question for you. So see, these things are still there for your reference, but I added this question. What is the sign of EMF when you travel? Oh, clockwise was already there. I already assumed clockwise. So let's say this is counterclockwise, okay? Clockwise, CW, counterclockwise. So let's suppose, oh, was that clockwise or counterclockwise? That is still clockwise, right? So counterclockwise should be something like that. So now I'm opening the poll. So go ahead and poll. So 30 seconds for this. Remember, I'm polling for counterclockwise. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so what we got here? So we have positive and negative. Okay. So when we went clockwise, it was positive. Now, when we go counterclockwise, what happens? See, we are going from higher to lower, okay? So initial is higher, and final is lower. And change means final minus initial. So final is lower. Let's say this is 0. So this is like 0 minus 12 gives you negative 12. Okay. So this is going to be negative that way. So which way we choose, which way in the loop we go is important. So that's why we need to first identify the loop. Okay. So looks like the correct answer in this case is negative. And when we went all the way around, it was positive. Okay. Are you guys paying attention? I hope so. Okay. So let's check. I have another question. So again, clockwise, no. Let's say counterclockwise. Okay. So that means this way. You are going in the loop like this. This is our loop. Okay. So pay attention to the arrow, which way we are going, you are going. Okay, so I'm going to open the pool and you have 30 seconds. And remember, current is flowing something like this in the loop and you are going this way. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so let's see what we got here. So now that seems to be a bit switched. Oh, that's interesting. 15, 22, 19. Okay, so 15 is still 15. Oh, that's interesting. So over here, what's happening? We are going this way. So current is going that way, means this is higher. Okay, so final is higher, means difference gonna be positive, right? When final is larger than the initial, the difference final minus initial is positive. So it's gonna be positive this time, okay? Okay, so now I have both of them at once. So what do you think? See, the loop is going this way, okay, for this one and that one. And here for the resistance, direction of current is given. For the potential or the source, current direction is irrelevant, okay? And so I'm opening the poll and you have a minute and 30 seconds to answer this question. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So B and C seems to be popular. C is most popular. Okay. So here we are going this way. So first one is about potential. So we are going this way means we are going from higher. Remember, this longer line means higher and lower. So we are going from higher to lower. So difference is going to be positive or negative. So higher is, let's say, 10. Lower is, let's say, 2. So this is initial. This is final. How do I know this is initial, this is final? Because we are going this way. So initially we'll encounter this. Finally, we'll encounter that. Okay. So that means this is like saying, okay, 2 minus 10. Final minus initial. So this is negative. So this has to be counted as a negative. Okay. So that means this is incorrect. This is incorrect. Now for this one here, so you need to remember that current flows from higher to lower. So this is higher, this is lower. And now initial and final, they are still same. We are still walking this way, right? So that means what happens here? We are going from lower to higher. So final is higher in this case. So it's like saying 10 minus 2. So positive. Okay. So it looks like B is correct answer. Oh, a lot of you thought C was correct answer. So IR is not always negative. It depends on how we are going. Okay. Anything you like to ask here, especially because a lot of you made mistake. What is problem? So where is initial, where is final, where is higher, where is lower, right? So that gives you change. It changes positive or negative. So you need to pay attention to that. Okay. So there is a question, how do you know A is higher in value than B? Is that assumed? Higher in A, so you mean that one here? So that's why we need to remember, recall. So negative terminal means lower. Negative has lower potential. Okay. And positive has higher potential. And probably you are wondering why there is no positive or negative. Yes, the positive and negative always not going to be there. Longer line means positive. Okay. See, the battery or cell has the symbol. One line is shorter than the other one. Okay. So we need to keep those things in mind. Okay. Longer line means positive, and positive potential is higher then 0 or negative. Okay. So now here is yet another question. So now see there is one source, there is another source. So we can write loop rule out of it. Okay. For example, we can choose one loop here, we can choose another loop here, we can choose this thing as a whole another loop. Okay, so we can do that, but let's start by just choosing one first. So here the loop is going something like this. So this is counterclockwise loop, right? So you are including these three elements, 1, 2, and 3. So direction of current is shown and loop is given. Okay, so that means now you should be able to write loop rule. So you can start from, looks like R2. These are started from R2. So let's say you start from this point. You don't have to, but the way they are, looks like we started from this point here. So you start like that and you go like that, right? What's going to be the equation for the loop rule? Okay, so I'm going to open the poll and you have 2 minutes, and I brought these things back just in case if you need to reread them. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So we have B and C bit popular, and B is more popular than C. Okay. So starting from here, so we are going in the direction of current. Current always goes from higher to lower. So final is, less than initial. So that means it must be negative. So it seems like in a loop, when we go in the direction of flow of current, that means that's going to give us negative potential difference. Okay. So this is going to be negative I2 R2. Now we are arriving here. It is higher. Positive is higher than that. So we are going from higher to lower. So difference is negative again. And then over here, we are going opposite of current flow. So we are going towards the higher because current always flows from high to low. So that means this must be positive then. So this sum must be equal to 0. So let's see if anything matches here. Looks like, yeah. So we are getting there, not quite there yet. Okay. So now let's say we are going in this loop like this. Okay. This is clockwise. That is loop 1. This is loop 2. So that's going to give us second equation when we write it. Okay. So can you type that on the chat? Type this equation like this. So while typing, you can type I2 as a this, I N2. It doesn't have to be subscript. Okay. And similarly, V1 can be typed as V1 like that. Let's see how many of you at least try. Okay. Don't worry about being wrong, but give it a try. Equation for this loop or loop 2. That's what I'm asking you guys to type. Okay. So maybe I'll take break here. We'll take break here. And when we come back, I'll give you a minute to type that equation. So now I'm going to write it and check if you typed it correctly or not. And if you did not, you know what to do. Keep practicing. Okay. So where should we start from? We can choose any point. That's fine. It does not matter where you start from. So for example, if I was to start from here, and this loop is going like that, means I'm going from lower to higher. So the potential has to be positive. Whether you write that as a first term, second term, or third term, just does not matter. But it has to be positive for this loop. And here loop is going in the direction of flow of current. So that means it's going from higher to lower. So difference is going to be negative. And then this one, same thing. You are going in the direction of current flow. So current goes from higher to lower, means difference is negative again. Looks like both current terms going to be negative. Now, let's say if I were to reverse the loop, right? Direction of current flow is labeled already. But let's suppose now we are going counterclockwise. How that's going to change, okay? So sign of all these going to change. So when sign of all of those changes, that means in an equation is like saying nothing changed, okay? So for example, if I do this, then now we are going from higher to lower for the source. So source is going to be negative. And then this now we are going opposite of flow of current. So that means it's going to be positive. And over here, again, opposite of flow of current, right? So that means it's going to be positive as well. But mathematically speaking, these two equations are same, right? I can multiply by negative sign on both sides. So negative 0 is still 0. So when I open this parenthesis, this becomes positive, this becomes negative, this becomes negative. So which way loop we choose does not make difference, okay? But once we have a loop, we need to be able to write it correctly, okay? So that is that. And now we can have third loop, for example. This all the way this outer loop, let's say. Starting from here, let's say, start here. So that means it's going to be in the equation, this is going to be in the equation, this is going to be in the equation, and this is going to be in the equation. So there are going to be 4 terms, right? So inner loop, they had only 3 terms, but the outer loop has now 4 terms. It's going to have 4. Now, which one is positive? Which one is negative? So maybe I'll let you do that, okay? And later or tomorrow or sometimes, if you want to show me your work, draw this outer loop and draw a loop like clockwise, just like I drew. Did I draw clockwise loop? I think so, yeah. That's what I did. And then write the equation. That way I can see what you are doing and can tell you are doing right or wrong, okay? So now, moving on. So source, we said, was, okay, usually ideal. It has negligible internal resistance. But let's say if we cannot neglect it, even if it is small, and say, okay, you cannot neglect it, you need to take account of this, right? So how do you do that? How do you include that? So basically what happens is when we say internal resistance, we can say, okay, inside a battery, there is a resistance. And usually that internal resistance is denoted by lowercase r, okay? So that means now you can replace a real battery by ideal battery plus the resistance, okay, in a circuit. So that's what you can do. And we have already seen this circuit, and we also wrote the equation for that. Okay, so it looks like here I am going clockwise in the circuit here. Okay, so now what happens is part of that EMF drops in that internal resistance. So you have this. And because of that, the potential difference available to the main resistor or the device in the circuit is now less. Less by how much? As you expected, less by the amount that drops in the internal resistance. Okay, so battery itself is consuming some energy. So that's why the battery gets warmer. Okay. So that's how we know it's consuming some energy on its own. Okay. When we connect a battery in a circuit, what happens? The battery becomes warmer as well. So for example, your phone, when you are using, let's say, some app that uses, bit power, for example, playing game and so on, when you are using your uh, phone, you may feel that warmness. Your phone becomes warm. So warmness does not just comes from the battery being warm, but other component may also get warm. But main could be the just battery being warm. Okay. So now this is the potential difference across the battery. So that's what we say. And this is EMF of the battery. So when there is internal resistance that we cannot neglect, in that situation, the potential difference in EMF, they're not going to be same. And how much is the difference? That is given by this over here. Okay. So now, especially when there is large current is flowing, what happens? Even when this resistance is very small, let's say if large current is flowing, then there are going to be some substantial amount of drop. Okay. And when large current flows through this, when large current flows through the circuit, when main resistance is relatively small. So for example, let's say if there is only 1 ampere current flowing, and let's say this resistance is 0.1 ohm, then how much energy drops? I times R are gonna be 0.1. Okay, so that's gonna be the potential difference, drop in potential difference, that many volt. Okay, now let's say same resistance, but let's say the circuit is drawing current as 20 ampere. And usually the case when we are using, let's say, our appliances in kitchen. Some have 40 amperes, some have 20 amperes current flowing through them, okay? So in that case, what happens is now the potential drop in the internal resistance, let's say of the source, gonna be I1 times that R, which is now 20 times 0.1. So that means it's a 2 volt. See? So let's say you said, okay, I'm connecting 20 volt battery or 10 volt battery, let's say. Then now how much voltage it's giving to the let's say appliances, to the load, sometimes we call it, or that big resistor. It's giving you just 8 volt. See, there is substantial change. But when current is flowing small, it's just changed by 0.1. So we can say, okay, in that situation, it's negligible. So even the same amount of resistor could be sometimes negligible, sometimes non-negligible. So the device that uses a larger amount of current, in that case, what happens? Internal resistance becomes, internal resistance is not negligible. But if we are using battery in a circuit where there is just tiny amount of current flowing, then it's not that a big deal, okay? So just like we can connect resistors in series and parallel, we can connect battery in series and parallel. So in our flashlight, we always connect them in series. So when we connect them in series, what happens? The EMF adds up, okay? So when we say series, see the negative and positive, see they are touching each other, right? If you don't make this kind of connection, and if you reverse this battery and say this is negative and this is positive, let's say, then what's going to happen? This 1.5 volt acts like a negative compared to this one, so they cancel, giving you the net 0. So that's why when you connect two batteries in a device, let's say in your calculator or flashlight, then in that situation, what happens? If you don't orient them properly, in that case, it does not work because the total EMF, one and other, they are canceling when there is reverse polarity, okay? So they have to match like this, okay? So in series connection, the polarity could be reversed or, not reversed. Let's say when we connect something like this, positive, positive in one direction, right? Not flipped. Then we say, okay, that's polarity is good. So in that case, what happens? The EMF doubles. But at the same times, now this one has an internal resistance and this one has an internal resistance. That means in a circuit, it's like having two resistors, internal resistance in series. So because of that, the current cannot double. Current does not double compared to the current from just one battery. Why? Because this resistance, internal resistance increased. So because of that, current becomes there. So if the, look at this here, it became E. The font supposed to be this side, this kind of EMF, right? So if there was only one battery, the current would be EMF over just R. Now, when there are two batteries in series, with the good polarity, correct polarity, I should say, the current you expect, let's say you expected this current 2 times EMF over R. That does not happen because now there is another R over there as well. Okay. So when there is no external resistance, it becomes even worse. But usually this resistance is very large compared to the internal resistance. So because of that, current increases, but it does not double. Okay, because this internal resistance now in series means the total resistance in the circuit is now, you know, larger than before. So in this circuit, if there was just one of these, let's say, then the current would be this. But now with this here, with both of them, we have, oh, we have 2R and EMF. Sorry, 2R plus the bigger case, uppercase R. Oh, that's what this is, okay? So you can see here, this I new is not double of I. And why that happens? Because of the internal resistance of battery. So that kind of combination is series. And we can have parallel combination. Often it's not used because EMF remains same, okay? When you connect like that, the EMF remains same. But one advantage is that equivalent resistance, oh, equivalent resistance now is smaller, right? When they are in parallel, equivalent resistance becomes smaller. So for example, if we have two of them, let's say, and this is just R, this is just R, then the equivalent R equivalent gonna be half of those. So because of that, what happens is it doesn't allow internal resistance to increase. But the problem is the EMF is still EMF, just one, even when you are connecting a lot of them, because they are connected in parallel. So this EMF, this EMF, this EMF, this EMF, they're going to be all of them same. So eventually in a circuit, it's acting like just one EMF, one battery. Okay, that's how. And of course, they're going to be internal resistance going to be smaller. Let's say if there are two, and that's going to be that and like that. So yes, current will increase a little bit more, but it's not going to double or triple or fourfold depending on how many the batteries are there. Okay, so that is batteries in series and parallel. So what do you think here? 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we get here. So C is more popular, so A is off and B is brighter. Okay, and A is brighter, D is equal. Okay. So in this case, what do you see here? These batteries are reversed. So that means if each of them have EMF that, then this is going to have, let's say, negative, and this is going to have positive EMF. And here, let's say this is positive EMF. So if we add EMF, what's going to be total EMF? Remember, they get added. So total EMF is going to be positive E in this case, just like this. So EMF is same, and bulbs are identical, means they will have equal brightness. So just reversing battery does not turn things off, okay? And so here there are 3. If there were just 2, then in that case, like in a flashlight, usually there are only 2 batteries, okay? But if you have a flashlight that takes 3 batteries, and if you put something like this, then what's gonna be the result? It's gonna be dim then when you put them, correctly, but it's not gonna be off. So it is like just having 1 battery, right? So D is correct answer in this case. Oh, it's harder than I thought it would be. Anything you like to ask? What may have caused problem? Still not sure about it? See, the inside the battery, I mean the they have, let's say, in a battery, electrons or charges can still flow because this is going to be driving here, okay? There's going to be net electric field that drives the electron. There is potential difference, means there is still electric field, and that is still pushing the electrons. So now with that, here let's say include. And internal resistance is also identical, okay? Same, all of them have R, let's say. How this answer gonna change or gonna be same, okay? So this time you have a minute to answer this question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got here. Okay, B got a little bit more, but C there. Okay, so now what happens here is EMF, let's say, is that. So they're going to be still same. So EMF is still that, but internal resistance here is R. But over here, internal resistance is going to be 3 times R. Okay, internal resistance, they don't cancel. So internal resistance higher here, but same EMF means less current. Means less brighter. Remember, brightness comes from power, and power is given by I squared times R, right? So yes, so this gonna light up, but B gonna be brighter because there is more current flowing through this because of less internal resistance of the battery. Okay, so B is correct answer in this case. So just like we can connect batteries in series and parallel, we can also connect the capacitors in series and parallel. And this is series connection. Oops. This is series connection and this is parallel connection. But if you look at equation, what happens? They are kind of opposite of in the case of resistors, right? So when resistors connected in series, and by the way, this is series connection. So resistor in series, what happens? R equivalent is R1 plus R2 plus R3 and so on. And R in parallel, R equivalent is 1 over R equivalent is 1 over R1 plus 1 over R2 and so on. See, in case of capacitor, those equations are kind of reversed, okay? So that's all I'm going to say about this. And now moving on. So in a circuit, we want to measure current and voltage. So the device that we use to measure current is called ammeter. So these days, there is just one device that can measure current, voltage, resistance, and everything, right? That's called multimeter. But when we are using, let's say, a pointer for the ampere or current, then we can say, okay, it is acting like an ammeter. So when it is ammeter, what happens is you need to open the circuit and connect it, okay, to measure the current. So that current has to flow through the meter. And meter also has some resistance, but this resistance has to be very small because when we are measuring, when we are using measuring device, we don't want that to change the current. We just want that to measure the current. So it's going to change, but it's going to change very little if it has very small resistance. So that's why they have to have very small resistance. So ammeter, if you want to measure current over here, then you need to put ammeter somewhere there in that area. If you want current through R2, then you can put ammeter either here or there, but putting there not gonna work. And same thing goes with that. So that's the ammeter. And now if we are measuring voltage, so remember, so when we say it, we say, okay, current flows through, oh, it's written here, the wire. And we say voltage is like a potential difference between 2 points, okay? It's a potential difference between 2 points. So that means it's not voltage across, okay? It's a potential difference or voltage. Yeah, I think it's a voltage at R1 or something like that. Okay, so we say potential difference is between 2 points. So we connect the voltmeter probe at the 2 points where we want to find the potential difference. Okay. So for example, if we want to find delta V1, which is voltage across R1, then you need to connect voltmeter like this. So now voltmeter have to have very high resistance, because if it has low resistance, then current will start flowing through that, means the effective resistance is going to be smaller. Remember, when we connect two resistors in parallel, and then the effective resistance becomes smaller, so the circuit starts drawing larger amount of current. So that's why the voltmeters, they have to have very high resistance. So usually they are in hundreds of mega ohm. Mega means 10 to the power 6 ohm. Ammeter, on the other hand, they have less than 1 ohm resistance. Okay, so that's how much different they are. So when this resistance is very high, so for example, let's say this was infinity, and what's the equivalent resistance now? So 1 over R equivalent is 1 over, let's say, whatever that is, R1, plus 1 over whatever the resistance of the voltmeter, and for, like, let's say, uh, for convenience or to easily see it, I'm saying that's infinite. So 1 over infinity is 0. So that means 1 over R equivalent is 1 over R1, means R equivalent same as R1, assuming that this one is not there. Okay, I'm just talking about one resistance and the voltmeter. So that's how it works. But in practice, what happens is we cannot have a number infinity. But just like I was saying, we can have this 10 to the power 6, but let's say this is 2, then what is equivalent? Equivalent gonna be still very close to 2, slightly less than 2, or maybe 0.00001, something like that. 5 after 5 decimal points, something like that. Oh, hold on, hold on, hold on. It would be 1.9 and then 0.001, something like that. Okay, still, oh, I think there would be 9999, something like that. Very close to 2. Feel free to punch in your calculator if you like. 2 times 10 to the power 6 divided by 1000000012345. I think this. So we are dividing this by this plus that, 1,000,002. I hope I wrote that correctly. Yeah, something like that. So it does not change much, okay? Just a little bit. So that's how that is done. Now, capacitors. When we have a battery connected to a capacitor and resistor, what happens is when there is no battery, then the resistor, let's say light bulb has a resistor, so it's easy to see when we have light bulb. And when we connect that, what happens? Light bulb first, it's light up bright, but quickly dies down. Okay, so the brightness decreases exponentially. Here I have a video. So there is this tiny bulb. It's like those Christmas light bulb, and the potential across that is being measured over here. Okay, and see how the potential gradually decreases. At the beginning, it quickly decreases, and then it slowly decreases. We call that exponential decay. Okay, first quickly and then slower. So it follows the exponential decay. See here. See how the brightness kind of dies down, and this voltage is now taking way longer to cross from that 3 to 2. So it's taking forever. And if you wait from 2 to 1, it's going to take even longer. And see how the brightness is similarly decreasing down because potential difference. See, this meter is measuring the potential difference across this potential difference between two terminals of this bulb. So it's taking forever. So this kind of decay is exponential decay. So we can represent that kind of thing. So for example, let's say this capacitor is fully charged, and then you connect with light bulb that has a resistance R, let's say, and turn on switch like that. And then now what happens? These electrons from the negative terminal goes to the positive terminal, or current goes other way around. So current starts flowing. At the beginning, there are a lot of charges. Oops. At the beginning, there are a lot of charges. It means larger current flows at the beginning. So whatever current flows at the moment you just make the connection is what we call maximum current. And then after that, what happens? It exponentially decreases. And that exponential decay is given by this equation where this I is current at some time t, anytime t after it's been connected, is equal to the maximum value of current. And this is the what we call exponential decay. And there you see this is time, of course, but this is what we call time constant. So this time constant depends on the value of resistance you have connected and the capacitance of the capacitor. So product of these two gives you what we call time constant. And by the time constant, what happens? About 66% of this thing has decayed. Okay. So that means the value is that, and the just like pi is 3.14, this E is also a natural number, which is 2.7 something, okay? Something like that, okay? So it is like you are dividing by almost by 3, right? The maximum value by 3. If this was 10, so then this is going to be 10 divided by 2.7, or approximately 10 divided by 3, let's say, roughly speaking. And voltage follows the same kind of, decay. At the beginning, voltage across the capacitor is maximum, and then it decays like that, okay? And eventually, voltage becomes 0 once all the charges, go there and recombine. There's not going to be any charge between the plates. So that means potential difference also going to be 0, okay? And that potential difference, whatever there is, going to be same as that. So that means potential difference across the resistance is also decreasing. So if I were to make a plot, the plot going to look just like this. But here you may want to plot voltage, and you say, okay, the maximum voltage we had in the capacitor, and so on. So basically same thing. And equation also going to be exactly same. Simply replace this I by B, Bm, right? So it's going to be exactly same equation for both voltage and current when capacitor is discharging. So why is discharging? It was full of charges at the beginning, and now there is no charge when at that time, okay? Just like we saw in that video. Now, over here, when we are charging, the voltage and current they kind of follows the opposite kind, but both of them are still exponential. Oh, this is supposed to be EMF here, maximum value. Okay. So over here, what happens? Charging means at the beginning there is no charge. So when you close the circuit, what happens? A lot of charges rush to occupy these plates because it's empty. So just like you have empty stadium and then people first let you go, what happens? It fills up quickly at the beginning and then it becomes slower and slower, especially if the, like let's say the ticket is not assigned there. I mean, seat number is not assigned. You just let the people get in the stadium and sit. So they're going to look around and try to find a spot and then sit. So at the beginning, there are a lot of empty spots. So quickly fills. Same thing goes with the capacitor as well. Okay. So now how about voltage? So at the beginning, there is zero charges means 0 volt at the beginning. Okay. Or let's say V is 0. So that's why you see this graph of the voltage starts from 0. And when it is fully charged, that's going to be equal to the EMF of the battery that is being used to charge. Okay. But in case of current, what happens? It's like a charging, discharging as well. What happens at the beginning? Large number of charges, like rushing first means a lot of current flowing at the beginning. So that's going to be the maximum current the moment you turn on the switch, and then it exponentially decreases. So this current is same, pattern of the current is same for charging and discharging, but voltage is slightly different. Okay. So over here, there is a question related to that. So it says, what is the time constant of this circuit? So R and C are given, so we should be able to figure that out, right? So R is 2 kilo ohm. Kilo means 1,000, so 2,000 ohm. And C is nanofarad. Ooh, 10 nanofarad means 10 to the power 10 times 10 to the power negative 9 farad. So tau gonna be R times C. You just multiply them and the product gonna be in seconds. Okay. It is a time constant. That's what we call it. Okay. If it stores 2 microcoulomb charge when it is fully charged, what is the voltage across it? Okay. So when it is fully charged, what is the voltage across it? So voltage, when it is fully charged, so in this case, we are given the, let's say for part A, Q is given 2 microcoulomb. So that means 2 times 10 to the power negative 6 coulomb is given. Okay. And capacitance is given, which is same for both cases. Capacitance does not change depending on how much charge you have, right? Still that capacitance is, is a capacity, like a capacity of a garbage can, I said. So now with Q and C, we know we should be able to figure out the potential difference. So we learned that Q is C times delta V. So that means delta V is Q divided by C. So both numbers are there. So we should be able to do that. So now in C, it says, okay, at what time T is equal to what? The voltage becomes quarter of the maximum voltage, okay? Oh, quarter means I should be writing 4. So for that, we want to use this equation, see how the voltage is changing here. So we want to use that. So B max is here, right? So that's that. And we want to find the time when this becomes exactly equal to the quarter of that max. So let's say B max over 4 is B max, whatever that is, 1 minus and T over tau. So the B max cancels. So only unknown is this T. So T is what? So that's what it is asking you to calculate. So to do that, you need to use, probably you have to take log after you rearrange, okay? So that the E thing goes out, the log of E T tau becomes simply tau over tau, okay? So that's the property of log with this E base. So at one point you have to do that. So num are going to have log, and your calculate should be able to calculate the log of that value. So since it is already 53, I already kept you longer. I'll let you go, but that's how this calculation is done. Okay. Okay, folks. So feel free to ask me if you have question, or else feel free to leave. I'll see you next week.